Hey folks, Mr. Mullett here. Just wanted to say hello and thank you for coming to science today. Today is your third day of science. Um, Please do ignore the backgrounds as I'm doing this down in the basement while everyone's sleeping. Obviously I'm not here again, so note that this is day 3. The date might necessarily match up, but the day will be valid. So if you've seen me 2 times already, you should be on your 3rd day. And if you haven't seen the 2nd or the 1st day, you should be seeing those before this. So let's get right into it. Again, thank the guest teacher for covering, and here we go. So one thing I want to start off by mentioning here is in the news, a couple of weird things have been floating around. One being that 2015 brought some weird weather thanks to El Nino and other factors. You'll notice there on the screen it says the North Pole had a 40-degree Fahrenheit temperatures. There was some extreme flooding across the globe and some record storms all contributed to making 2015 a year of weird weather. While the year is coming to an end, the weird weather is here to stay. 2 factors are contributing to this, include the El Nino and a strong Arctic oscillation. This is what has kept all the cold air up in the Arctic, giving us that really, really warm December. That shows no signs of letting up in the first month of 2016. Obviously, it's definitely gotten a little bit cooler over the next couple of days, but that's not for forever. Scientists are predicting another year of record heat and some more bizarre weather events. So, just some news for the people who like to pay attention. All right, next up, same deal. Your sea layer is still due January 11th. That's Monday, and also your vocabulary quiz will be Monday, Tuesday of next week. So keep that in mind. Keep practicing those vocab puzzles. Our agenda, it's a little bit longer today, so this may be a 2-part video. Again, vocabulary puzzle, I would recommend for those who are doing really well in this, just go along with this. If the whole class is doing really, really well and everyone's getting their puzzles completed in sub 5 minutes, as a class, you can elect to only put the puzzle together once, while the other classes may elect to put it together twice, maybe for a total of 10 minutes. As a class, you guys need to make that decision. So, vocabulary, you guys should know how to do this. Again, this does involve using the online timer, counting up, get that going. All right, I don't need to show you that. So, next you'll notice energy movement on Earth, that's your CCR. We will take a moment to go and talk about that. And hold on, let me just hold on here. Sorry about that, you guys. I did receive a phone call, so I apologize. At any rate, I was talking about we were going to be discussing energy movement on the Earth, that involving the CCR, conduction, convection, and radiation. Some of this should be a little bit of review of 7th grade, but this is my job to go over it again with you, as well as apply it to the atmosphere, as well as plate tectonics and the Earth, as well as just conversations pertaining to everyday movement of energy on our planet. You're also going to notice I'm talking about the electromagnetic spectrum, albedo. We'll talk about that in a little bit. There will be a short little journal entry for today, as well as 3 more topics, one being positive feedback loops, direct and indirect lights and seasons, and last but not least, fronts and air masses. So, here we get going. First and foremost, again, you've taken care of the vocabulary, and our objectives are not changed. A reminder of all the different spheres that make up our planet. And here we go. So, for notes purposes, I'd make the recommendation that you pause the video after I highlight everything that's going to be listed here. And if anything, you could actually go and wait till the next slide so that you can go and address each one of these individually. So, you'll notice here we have conduction, convection, and radiation being listed. There's your CCR. You're going to see this listed on every slide, so you only have to list it maybe once. But please remember, anytime you move energy, there's always some loss. So whether we're talking about the radiation that you see coming off of the fire here to the hands, the convection as hot air rises, or the conduction as it passes through the metal to the hand over here, the gloved hand, there is always some energy that is lost. Now, it is not destroyed and it is not created. That's the law of conservation of energy. But more importantly, it usually changes form. And we'll go over some examples of that in a moment here. So, first up, conduction. Where would I start with my addressing of the notes on this? I'd probably start by just simply going and getting the definition here. Let's see here, highlighter. Come on, you. There it is. I would highlight the word conduction, get that going there. And sorry here, changing my highlighter width. There we are. All right, so conduction. This is huge. It has to be direct contact. If you don't have direct contact, there's no conduction occurring. So that's the first one there. Next up, ways of thinking about it. I think of a band director like Mr. Belargin or Mr. Gomes, where they literally are figuratively trying to remain in direct contact with the musicians by use of the baton, which he holds in his hand usually. You can use the band conductors as a way to remember this. Or you can think of train conductors. A train conductor needs to go and literally physically hold your ticket and punch it to validate your ticket. However you choose to get there, it's all about conduction. So a great example might be that when you touch a really hot pan and that transfer of energy goes right, the heat goes right to your fingertips, possibly melting your fingertips and skin off. That's conduction. So that's always lovely. Over here on the side, let's see. Again, a reminder, there's always loss. So I'm going to go and say go ahead and take a moment here and get some of the key heat items here, mostly due to direct contact for sure, band conductors or train conductors, and that there's always a loss. Have that at least once on these lists. All right, you can go ahead and pause. All right, you've obviously come back from pausing, and let's get into the next slide. All right, next up, convection. All right, so this is your second way of moving energy. Convection, I'm sorry that a lot of you haven't grown up with this awareness, but convection ovens, you can ask Mr. Mullett, who's in front of you right now. He did spend plenty of summers working at a lovely ice cream shop called Ben & Jerry's, and in there, well, he had to make brownies in the morning. Convection ovens were something he can use, and basically he can explain to you what he saw when he opened the ovens, but if you wish, in the upper right-hand corner is a nice little picture here showing a fan in the back of the oven to go and move that heat around. So it's not just this constant flow of heat rising up, so the bottom of the pan is hot. It's actually being spun around. So what am I looking for here? Well, convection, for sure. You want that. The word convection is used to describe movements of heat through fluids. Now, some of you may or may not know this, but the word fluids means both gases and liquids. All right? It's not just liquids. So a fluid is anything that can take the shape of the container it's being poured into. You may not realize this, but you can pour gases into containers and they'll take their shape. So by definition, gases are fluids. I mentioned convection ovens being used. If that doesn't make sense to you, you can skip that one. Definitely though, convection currents. This we're going to see here. You think of this picture up here where the inner core and the outer core are very, very hot, and that heat is rising up from the core, out to the surface of the crust, and then back down again as it cools. Well, gosh, the Earth's core is an example of convection currents, as well as hot air. Think of a hot air balloon wants to rise, or in this picture here, we've got two pictures showing a hot air over land rising and cool air over water falling, and then the reverse occurs at night, where the warmer water, warmer than the land, heats the air rises, and cool air takes its place. We're kind of basically explaining to you how wind forms, which we'll chat about a little bit later, but understand that it's these convection currents that move this warm air or warm earth. And last but not least, for those of you who have ever had spaghetti or pasta, if you ever watched a pot of boiling pasta, you see that the pasta rolls to the surface, boils to the surface, and then falls down the sides, or maybe reverse. But at any rate, you do see this rising and falling of hot water. So kind of keep that in mind when you're thinking of convection. Go ahead, pause. Sweet. All right, so here we are. We're done with convection. Let's get to the next one. Last way of moving heat energy. This is radiation. Now, this one is going to be huge because no matter how you slice it, no matter where you look at it, the majority of the energy that we consume here on planet Earth, whether it's food, electricity, or some other type of energy, it originates a lot of times with the sun most often. And so we're going to start off by talking about radiation as being a form of energy, radiation, that is transferred by means of EM waves, that being electromagnetic waves. This energy is carried in wave format. The waves are defined by varying wavelength, so we don't need to get too much in that. Just know that different wavelengths are how we identify different waves. Some of the key waves to think about: ultraviolet, gamma, and X-ray are on the dangerous level, and Excuse me, the other ones like visible light or radio waves, microwaves, not so much on the dangerous side, but in certain doses and under certain circumstances can be quite harmful to you. We might even get a chance to talk about microwaves in your cell phones and so forth. So go ahead and pause so people can get this in their notes. Sweet. So we're done pausing. Alrighty, here we are. So there's a nice little picture to show radiation. This is an EM wave, ladies and gentlemen. You'll notice here that there's a magnetic field in blue and an electric field in red. They are 90 degrees to each other, but they work in conjunction to produce what we refer to as an electromagnetic wave. Cool stuff. Don't forget, wavelength, crest to crest, as defined by this Greek letter called lambda. Again, for those who love to chat about it, lambda, I always think, and my brother may or may not agree with this, lambda, that was the name of the fraternity for the nerds in Revenge of the Nerds. They were the Tri-Lambs, or lambda, lambda, lambda. Their Greek symbol literally was this. Science and Pop Media. Okay, so here we go. Let's get into something else. Now, seeing all three in action. This is going to be kind of huge, and I do hope that this picture is not in the way. I'm thinking it should be out of the way, but I could be wrong. Who knows? Here we go. All right, so we've got a lava lamp, and I love using lava lamps. Lava lamps are perfect for going and showing how all three of them work together. So I'm going to do some identifying here. And start off by just making this a little bit bigger. I'm going to label three parts. I'm going to label this part right here. And I'm going to label this part right here. And I'll explain each part in a moment. And this part right here. Now, you may notice this as being March 16th, 1971. This gentleman here was the first to patent the quote-unquote groovy lava lamp. And the lava lamp went on, obviously, to become quite an iconic item. But it is actually patented, and actually, you notice that the patent is 1968. But let's go and talk about how all three of these items show up. So we have parts A, B, and C. Part A is the fluid moving around. Part B is this metal coil right here that, while not touching the light, is in direct contact with both the glass and the fluid touches it as well. And last but not least, you get this light bulb down at the bottom. So let's go and identify the different parts. Part A. What is part A? We're talking about the movement of fluids. Hot fluid rises, cool fluid falls. Which one would that be? You've got radiation, conduction, or convection. Which one? Thoughts? It's convection. So A is convection. All right, part B. You may remember that I was mentioning a direct contact a bunch of times with this metal coil. And it's kind of hard to see, but there's a metal coil right here. And if you look at a lava lamp, you will see this metal coil. So if it's in direct contact, what's that going to be? Good job, class. Conduction. All right, that leaves us with the last part, the light bulb. That's going to be visible light, infrared waves giving off EM waves. So which one is that going to be? Last but not least, obviously, that is radiation. Make sure you go and put this in your notes, folks. Pause the video, get this into your notes, draw yourself a lava lamp, and label all three parts, please. Excellent job. All right, so we pause. I'm going to say that this is going to be the end of part 1 of this video, and I will come back for part 2 as soon as the video loads. Thanks, guys.